Welcome to the lesson on vehicle-to-everything technology. By the end of this lesson, you will be able to clearly explain what vehicle-to-everything, or V2X, communication means and why it is important. You'll be able to differentiate between the different types of V2X, such as vehicles communicating with other vehicles, traffic lights, pedestrians, and networks. You will describe the main components that make this communication possible, including onboard computers and wireless systems. You'll compare the two communication approaches, cellular networks and direct short-range systems, and explain their differences. You will also identify the challenges that slow down adoption and discuss how V2X technology may continue to improve in the future. Imagine driving through a busy city street. A car in front of you brakes suddenly. At the same time, the traffic light ahead is about to change. A pedestrian steps into the crosswalk. Normally, drivers react only after seeing these events. But what if your vehicle already knew this was going to happen before you could see it? What if cars could share information instantly with each other and with the road around them? That idea is exactly what vehicle-to-everything, or V2X, is about. It allows cars to communicate. Instead of driving independently, vehicles become part of a connected system. Now that we have pictured the scenario, let us clearly define what V2X means. V2X stands for vehicle-to-everything. It allows vehicles to send and receive information from other cars, traffic lights, pedestrians, the internet, and even the power grid. In simple terms, cars are no longer just machines that move. They are connected systems that exchange data in real time. This communication creates what is known as a smart transportation system. Instead of reacting only to what the driver sees, vehicles can anticipate situations using shared information. This improves awareness beyond line of sight and helps transportation systems operate more intelligently. Let us look at the different ways vehicles communicate. There are several types of V2X communication. First, vehicle-to-vehicle, or V2V, allows cars to warn each other about dangers such as sudden braking or obstacles. Next, vehicle-to-infrastructure, or V2I, enables cars to communicate with traffic lights and road signs. Vehicle-to-pedestrian, or V2P, helps vehicles detect and alert people walking or cycling nearby. Each type focuses on sharing information between vehicles and a specific surrounding element. Together, they create layers of safety and coordination on the road. In addition to those direct road interactions, vehicles can also communicate beyond the roadway. Vehicle-to-network, or V2N, allows cars to connect to the internet for services such as traffic updates and navigation data. Vehicle-to-grid, or V2G, is especially important for electric vehicles because it allows them to share electricity with the power grid when needed. Vehicle-to-device, or V2D, enables cars to communicate with nearby smart devices like phones or wearable technology. These additional forms of V2X extend communication beyond traffic situations into energy systems, digital services, and personal technology. Let us now focus on one specific example to see how this works in real life. Imagine one vehicle brakes suddenly on the highway. With V2V communication, that car sends out an immediate warning signal. Cars behind it receive that signal instantly, even before the driver sees the brake lights. This early warning allows vehicles to slow down more smoothly and prevent chain reaction accidents. In simple terms, it is like cars saying to each other, "Slow down, something is ahead." This type of rapid communication reduces reaction time and improves safety. Now that we understand what vehicles share, let us examine how they are able to share it. Each V2X-enabled vehicle contains an onboard unit, which is essentially a small computer. This system works together with antennas, a GPS receiver, and wireless communication modules. The GPS determines the vehicle's location. The antennas send and receive signals. The wireless connection transmits data to other vehicles or infrastructure. Together, these components function much like a smartphone built into the car. It processes information, determines relevance, and communicates important messages in real time. Vehicles are not communicating alone. The infrastructure must also participate. Traffic lights and road signs can be equipped with devices called roadside units, or RSUs. These units contain communication hardware that allows infrastructure to send and receive signals. For example, a traffic light can inform an approaching vehicle that it will turn red in a few seconds. RSUs act as communication bridges between vehicles and the road system. This allows transportation networks to become active participants rather than passive structures. Beyond vehicles and roadside units, there is another important layer supporting V2X communication. Some information is sent to cloud servers. These powerful computers analyze traffic patterns, process data, and send updates back to vehicles. Cloud systems help manage large-scale information such as citywide congestion or emergency routing. It functions somewhat like navigation apps, but with real-time vehicle-to-vehicle input. This broader connectivity makes transportation systems more responsive and coordinated on a larger scale. Now that we understand who is communicating, let us discuss how that communication travels. There are two primary ways cars communicate. The first is cellular V2X, which uses existing 4G or 5G cell towers. This allows long-distance communication and broad coverage. The second is direct short-range communication, or DSRC. In this method, vehicles communicate directly with nearby cars or roadside units over short distances. Cellular systems provide wide coverage, while short-range systems allow extremely fast local responses. Both approaches help create flexible and reliable communication networks. The most important benefit of V2X is improved safety. Faster warnings help drivers react sooner and reduce the chances of accidents. Better communication between vehicles and infrastructure also helps manage traffic more efficiently, allowing vehicles to move more smoothly and reducing congestion. When traffic flows better, gasoline vehicles spend less time idling, which lowers fuel consumption and reduces pollution. V2X also supports emergency response by alerting drivers about hazards, accidents, or dangerous road conditions ahead. Instead of vehicles operating independently, transportation systems become connected networks that work together to improve safety, efficiency, and overall traffic management. Although V2X offers many benefits, implementing it on a large scale presents challenges. Installing V2X systems everywhere is expensive. Not all vehicles are currently equipped with this technology, which limits effectiveness. Different manufacturers may use slightly different technical standards, requiring coordination. In addition, data security and privacy concerns must be addressed to protect users. These challenges slow adoption, even though the technology itself is capable. Looking ahead, continued advancements will shape the future of V2X systems. Faster 5G networks will allow more reliable and higher speed communication. More vehicles will become connected over time. Cities will increasingly incorporate smart infrastructure to support transportation networks. Automation in driving systems will also rely heavily on V2X communication. The overall goal remains clear: safer, smarter roads supported by coordinated communication systems. Let us now summarize what we have learned in this lesson. Vehicle-to-everything, or V2X, enables vehicles to communicate with cars, infrastructure, pedestrians, networks, and smart devices. Vehicles rely on onboard computers, antennas, GPS, and wireless systems to transmit real-time information. Communication occurs through cellular networks or short-range direct links, depending on system design and coverage needs. V2X technology enhances road safety, improves traffic flow, and supports emergency response. However, high infrastructure costs, technology compatibility issues, and privacy concerns currently limit widespread adoption. Continued expansion of 5G networks and stronger security systems will support future growth and advancement of V2X systems. Thank you for your attention.